We're at 3:30, perfect. So yes, today marks the last class, maybe for all of you, or at least some of you, that'll be virtual. And then we are going to have reading week, and then we're going to be back in person, sorry, looking at my calendar, on March 28th. For us, it'll be the 29th. It'll be our first class. So do make sure to go and check on Solus where your actual classes are, because now they are going to be in rooms and you'll have to find those rooms. So with no further ado, though, let's dive into our last topic for the remote portion of linear algebra. So here we are. We're starting what is in section 8 in the online textbook, and it's going to introduce more words, but fortunately, they're fairly intuitive words, as we'll see as we go through this. So we're not going to be looking at systems of equations. We did that. We're going to use it a little bit today, but mostly we're going to be talking about conceptual sides of vectors. And the idea is, if we have a vector space V, we can define a set of vectors. So this will be a set of vectors whose span is all of V. So a spanning set, you can kind of see the connection here. If you have a spanning set, that means you've got some building block vectors. These building block vectors that with those building blocks, you can reach all of V using linear combinations. So another way to say that here, every vector in the whole space, the entire space, all infinite number of them, is a linear combination of this, some probably finite building block set. Not always finite, but for the usual Rn kind of things, a finite set. And it helps to visualize this if we can. So we are going to think about the plane R2, and we're going to draw a bunch of different planes here. You know, our usual XY, XY, and XY. So spanning sets. Let's consider the option of a single vector. Okay. If I have a single vector like this, and let's call it V1, and I can make any vector I like, W, which is equal to AV1, let's call it A1V1, make any, can I reach all of R2 with that single vector? And I'm hoping most of you are thinking, well, probably not, because I can only go in this direction. I can only scale or reverse that vector. And so what the answer will be no to this. Let's get to here. This black line here is the span of the set V1. And that is not all of R2. And so the set V1 is not a spanning set for R2. Now, I think you can imagine, well, if I have more than one vector, all of a sudden we're in much better shape. Specifically, if we had two vectors like this and like that, two vectors, then all of a sudden I have a lot more options. I've added a direction that I can move in. And you can imagine picking any point, say up here, and I can get to that point through a combination of those two vectors, A1V1 plus A2V2. This can reach any point in R2. And so I should give these guys labels. This will be V1, that'll be V2. So the set V1, V2 here is a spanning set, or a, what do I call it, generating set. Generating set, and specifically for our vector space, so for R2. Okay. Now, can we have more than two vectors? Is that a problem? Well, I don't think so. If we have V1 and we have V2, and let's add V3, and why not? Let's add V4. V1, V2, V3, V4. This is also a spanning set for R2. I'll go through this whole shenanigans here, but I think you can see, well, if I have V1 and V2, adding V3 and V4 is just kind of gravy. I can certainly get anywhere I want with these two vectors. And so, yeah, adding more doesn't stop a set from being a spanning set. It gives us at least the same and possibly more directions we can move in as we add more building blocks. So with that all said, I'd like to think about it for a second. I'm just going to add a page here. Is it possible to have, sorry, take a step back. If you have a single vector, there's just no way that a single vector can span all of R2. And this is sort of a teaser for where we're headed with this, which is defining what we mean by dimension. We can know in formula what that is, but we're going to be able to get more precise about that. But basically, one vector cannot cover 2 dimensions of R2. However, if I have 2 vectors, can I always cover all of R2? Think about that for a sec. So certainly these 2 vectors, absolutely, they cover all of R2 if I'm allowing myself linear combinations. But is it possible to pick 2 vectors where I still can't get to everywhere in the entire dimension there? If you have a thought, I put it in the chat, feel free. But yeah, is there a set of 2 vectors that I could use that will blow things up? Exactly. Parallel scalar multiples. And let's just look at this example of two vectors in R2. And we're going to tie this back to our other stuff. So perfect. So we had V1, V2, V1, V2. That set V1, V2 does span R2. Whereas if we had 2 vectors like V1 and then V2 that are parallel, then V1, V2 here does not span R2. And so is not a spanning set, means the same thing. And what's the difference between those 2 cases here? These 2 vectors here are linearly independent, whereas these ones are linearly dependent. So there's something about that earlier idea about if the set of vectors, dependent, independent, somehow plays a role in how much we can cover in our space. So just keep that in the back of your mind as we go through this. The new concept, though, is just a spanning set. So a set of building blocks like V1, V2 that lets me reach the entire space, or a set V1, V2, V3, V4 that also lets me reach every single point in the space through linear combinations. All right. So nice, easy one here. Is the set 1, 0, 0, 1 a spanning set in R2? And so if we draw this, we can see this visually. Here's our X and Y. And so the 1, 0 vector is this one here. That's our 1, 0. And then our 0, 1 is this. And the answer, of course, is yes. This, this pair 1, 0, 0, 1 is a spanning set for R2. In fact, it's actually how we define R2 in terms of how many of this and how many of this. Well, that's what we often see in physics as the I vector and the J vector. And the implication is we can represent any XY point as W equals X times the I vector plus Y times that J vector, J unit vector. So it's X times 1, 0 and Y times 0, 1. So I can show it algebraically as well. You give me any point xy, I can reach it by taking a certain amount of x component and a certain amount of y component. So nothing new there. The follow-up question is, well, what if I add another vector to this? Can we still span the set? And the intuition is absolutely. Adding another vector to the set can't decrease our reach with those building blocks, can only increase it. Here it turns out not to make any difference at all. If we have the 1, 0 vector, the 0, 1 vector, and the 1, 1 vector, then this is still a spanning set for R2. In fact, any two of these would represent a spanning set because it's linearly independent. So I could take the 0, the 1, 0, and the 1, 1, and with those two, I could reach any other point on the plane. With these two, I could do the same thing. With these two, we already showed we could reach any point on the plane. So that's useful, just to get a sense of spanning sets. Okay, so someone gives me a collection of building blocks. Can I get to every place, every point in the space with linear combinations of those building blocks? Now, we're going to come, I hope you're feeling like, but there's a difference, right? This somehow is simpler and cleaner than this. This has some redundancy in it somehow. And so we're going to tease that out in a second, just to show that there's other kinds of spaces that we haven't really talked about as much recently, but that are worth thinking about when we're talking about the general linear algebra applications here. This set W, which is looking at functions that are continuous and infinitely differentiable. If we add the condition, I want all functions whose second derivative equals 0. That's what this condition here says, right? I've got f double prime equals 0. So I'm looking for any possible functions that would have a 0 second derivative. And so if we take examples of things that are in W, the function 1 is in W, the constant function 1. Also the constant function 10 and, pi and 73, all the constant functions are in W, because if I differentiate constant functions, I get 0 at the first derivative and the second derivative is also 0. Can you think of other functions that are also in that set? Again, feel free to just go into the chat there. Any other functions whose second derivative is 0? Linear, absolutely. X plus 1 would be in W, because if we take this, we call this f. Our f prime would be 1, and so our f double prime would be 0 of x. Perfect. Okay, and so that means, like 5x minus 9 is in W, and so on. So there are an infinite number of functions in W, right? Just even the constant functions, there's an infinite number of constants I could pick, all the horizontal functions. There's certainly an infinite number of linear functions on top of that. So there's infinite functions in W, but without proof here, I would argue that the set of, let's use the simplest possible one we have, 1 and x, is a spanning set for W. If I take, i.e., all functions with f double prime of x equals 0 are of the form, let's go, f of x equals a times 1. Oops. Displace that. There we go, to 1 plus b times x. So if I take any combination of 1, the constant, and the b function, b times the x function rather, then I'm going to get a linear function. And for sure, the linear function, when I differentiate it twice, is going to give me 0. No matter what the constants are, we know that 2 derivatives will always wipe that out. And so, yeah, this set of functions is a set of building blocks that will reach any possible, or help me build any possible function whose second derivative is 0. And you kind of see 2 derivatives, 2 constants. There's a nice relationship there that you've seen with integration, that kind of thing. But yeah, so we can talk about generating sets or spanning sets for sets of functions as well. So that's handy. But now returning to that earlier theme of somehow this set in R2, going back to regular 2 dimensions, somehow this set in R2 has some redundancies. And what does that mean for us? Well, it's going to be an important ingredient, and you'll hear this phrasing used a lot in EngPhys, the idea of a basis function set, or you'll often hear eigenfunctions used. They're going to be of the same ilk of a set of building block functions that's sort of minimalist. So when you hear basis, I want you to think of minimalist spanning set. So a basis is a new term, but it's just an extension of what we just saw. So it is a generating set or a spanning set for V. So it's the same as before. A basis is a spanning set, but it has this extra condition here that not just any set of vectors will do. The set of vectors has to have this non-redundancy that we see when a set is linearly independent. There's no extras just hanging around. This is a distilled or minimalist set. And we can compare and contrast that with those 2 examples we just saw, which is this one here. This is a spanning set plus linearly independent. Implies a basis for R2. This is. Whereas here, this is a spanning set. We saw that earlier. It's totally fine as a spanning set. It reaches all, those building blocks can be used to reach all of R2. But it's linearly dependent. Okay. How do we know that? Well, because if I take these 3 things, just tying back to what we know about linear dependence, there's that formula, which is if I take A times 1, 0 plus B times 0, 1 plus C times 1, 1 equals the 0 vector, I can get a solution to that that's non-zero. In particular, I probably went to the other side to solve it, but basically if I have one of these and I have one of these and I have -1 of these, I'll get 1x, 0x, -1x, that gives me 0x. I'll have 1y, -1y, I'll have, so that'll be a 0, 0. So this is a lovely set, but somehow it's not reduced down enough to be linearly independent. And so this is not a basis. It's a lovely set, but it's just not a basis for R2 because it does span, but it doesn't have a linearly independent nature to it because it's not linearly independent. Now I'm emphasizing this. You'll see in the web work problems. I think it's for week 7, which is going to span these 2 topics. This topic is going to span week 6 and week 7. You're going to see, is something a basis? Yes or no? And then the follow-up is going to be, yes, it is, or no, it's not, because no, it's not a spanning set, or no, it's not linearly independent. So that's going to be something you're going to play with in the web work. That's Friday. That's as good as it gets. All right. So looking at pictures again, this is a basis. This is not a basis. This is, you can imagine just thinking back down to your 2 vectors. There we go. Thinking back down to your 2 vectors, 0, 1, 1, 0. if I take anything away from that, all of a sudden I can't reach all of R2. So somehow those two vectors are sort of a minimal thing. They're not unique. For example, we could also have, the vectors 2, 1 and -1, 2. They don't have to be perpendicular. You could have these two vectors. Those are linearly independent and they will span all of R2. So this would also be a basis. Also a basis for R2. So a basis is just going to be literally any two linearly independent vectors in R2. In fact, it gets back to what we saw with this picture here. Any two vectors that are linearly independent are going to be a basis in R2. As soon as our two vectors become linearly dependent, then all of a sudden, now then they can't reach some of the space. We're going to lose actually both our spanning set and our linear independence. But these are the kinds of scenarios that we're thinking about when we're trying to imagine what a basis is with that. Now, I realized as I was looking through the notes today, I mentioned this just when people were coming in, that there's an important ingredient missing that was in the notes last year, and I don't know why I deleted them by accident, but it was clearly by accident because they should be there. So one of the things that we can do with a basis is develop a new coordinate system, and this is huge in physics. Physics. And anything related to physics. If you're talking about truss designs and things like that, being able to reorient your universe, put things in a different frame of reference is the term that we get used in physics a lot. We need to be able to translate from one basis to another basis, which is what we're going to try to do here. So a basis just provides a unique way to represent any vector in V. And what do I mean by that? It means that if we have any vector in the space, we can represent it as a linear combination of the building block vectors in the basis. We know that because there exists a solution. Sorry, put here. Yeah, I'll do it here. Actually, I'll do it in 2 stages. There's this question: the uniqueness of the representation, the fact that there's only one way to reach a point out in the space with these building blocks. The reason we can guarantee that there's only one way to do that, that it's a unique way to do that, we can say that because of the basis term rather than the weaker spanning set. And why is that? Well, because remember that if we have the set V1 to VP and it's linearly independent, then that means that the linear equations alpha 1 V1 up to alpha P VP equals W. Wait, what did we say about linear equations and independence of vectors? This has either a unique solution and that comes from the linear independence, right? If we have linearly independent vectors, we get a unique solution. Saw that 2 classes ago. Or no solution. Well, how do we know that there's just one and not no solution? Well, this is the other half of the basis. But a basis spans all of our vector space V, which means that any W in our space is a linear combination of the vectors, V1 to VP. Right. If we're saying, just like in R2, if I have my 2 vectors, here we go, I have my 2 vectors, I can get anywhere in the space. Well, I can get anywhere in the space. That means any point you happen to pick, doesn't matter where it is, it can be written as a linear combination of your building blocks. Well, that means this thing right here, this linear combination of my building blocks adding up to my vector is guaranteed because it's a spanning set. And so there exists at least one solution. So we're getting a nice tie-in here with our no solution means not spanning. Exactly one solution is when we have a basis, because it spans, it reaches everywhere, but it only reaches it in one way, unique solutions. And then if we have too many vectors in our set, then we can span everything, but we have too many solutions, we get an infinite number of solutions. So there's no uniqueness there. So, and yes, I will upload the cleaned up version of these files after the lecture today, absolutely. So the word basis is something we're going to use a lot. So some things have been kind of been silly, really. Bases are something we're going to use a lot in the course as a concept. It's this minimalist set that reaches everywhere in our space. All right. Now you see this, as I say, in physics, where if you have, regular xy, but then the prof comes along and defines an inclined plane, all right? Inclined plane. What you often have to do, this is no shock to exactly 0 people in this class after 111 and 112, is take things like, oh, I don't know, the gravity force. So imagine you got some block here. You're going to have the gravity force as a vector, and you need to represent Fg in components parallel to and perpendicular to the plane, right? If you're talking about normal force and balancing of the forces, or what's the net force pulling down, all that jazz, what you're doing under the hood here is you are representing the space in terms of V1 and V2, and you're writing this is equivalent to writing Fg as a vector is equal to A1 V1 plus A2 V2. And this is your V1 was parallel. This is your, this A1 here is your parallel to the plane component. And your A2 is your perpendicular to the plane component. And because of the properties we just talked about, it's sort of obvious in R2 that, well, it's unique. Well, if I take the gravity force and I project it and do all that other fun stuff that you do with vectors, we can project this onto the V2 line. We can project it onto the V1 line. We'll get components, in this case, both negative components, but we can do that. And what we're seeing from the linear algebra is that that projection is unique. There's only one way to get, there's only one possible tangent to the plane component. There's only one perpendicular to the plane component of gravity. And that comes from the linear independence of those two vectors and all this other linear algebra under the hood. And oh my God, yeah, so I just had flashbacks to all the different ways I've used projections onto spaces, onto bases in data analysis and with functions. Anyway, it comes up in a whole pile of different areas. But again, all you're doing is taking two vectors and finding the components that go with them. The shortcuts you'll learn about cosine and sine of the angles, all that stuff, they're just ways to get these numbers in an efficient way. The kinds of questions we're going to ask you in linear algebra are related to that, but just a little bit different. So hypothetically, say in a week 7 web work, So you won't see this over the break, but you will see it in next week. You have two vectors given to you, and it never hurts to draw it if you have the chance. So -5, sorry, x and y, -5, -6, so a little further down here. That's V1. I'm going to write it our traditional way, -5, -6. And something almost the same, actually, V2, which is -5, -5. They are linearly independent. In R2. And so we expect that we should be able to make any vector in the whole entire plane out of those two building blocks with linear combinations. And we're asked to build that the 0x minus 1. There we go. I want to build this vector. Horrible notation here with x being used twice, but there it is. I'm going to call it W to match what we did before. So I'd like to build the vector W out of those two building block vectors. Well, how do we do that? Well, we build it just with the math that we know. I want W. I want W as a linear combination. Let's call it A V1 plus B V2. W equals a linear combination of the vectors V1, V2. All right. And if I want those, well, then let's put in the numbers. I want the vector, now I'm going to stack them just because it looks nicer. W is 0, 1 is equal to A times the vector V1 minus 5 minus 6 plus B times the vector minus 5 minus 5. I'm just taking these guys and putting them into our slots here. Basically, how many of this vector and how many of this vector does it take to make this? That's all we mean by components in any sense. Usually it's the x component, which is the 0, 1, and the y component, which is 1, 0. But now we're just using two different building block vectors. And so, yeah, but you're still sure there. This has a nice simple solution, but I want to write it out in a way that we've seen just a little while ago. Hey, if I put this into, I'm going to make the left-hand side from these two vectors here, minus 5, minus 6, and then minus 5, minus 5. That's our A component, that's our B component. And I'm, oops, a little early there. I'm going to make this our augmented matrix system. This is our augmented matrix equivalent. So how do we identify these two components? We solve a system of linear equations, and it might be easy, it might be hard. Let's take a look. If we take, oh, sorry, minus 1, thank you. That, now I got you. I thought you were giving me a solution. Yes, minus 1. And minus 1 over here. Thank you. Minus 1 all the way through. It was correct in the diagram, but that value and that value definitely should be minus 1. Thank you for catching that. So finding the components of a vector in terms of building block vectors, in terms of basis vectors, is exactly the same thing as solving a linear system of equations, because we're looking for the multipliers that satisfy this equation. It's all the same stuff. And again, here's where our uniqueness and existence of solutions comes in. We know we are going to have a solution to this because these two vectors will span the space. They are a spanning set for the entire space. So I know there's going to be a solution. I can tell also that they're not multiples of each other, so they're linearly independent. And so there will be a unique solution to this. So all of that thought process can go on in the background. So we know what kind of answer we're looking for. We're looking for a unique solution, a specific A and a specific B that's going to make this work. So what do we get when we do this? Let's solve. And so we're going to take, let's take row 1 and just divide it by minus 5 and divide it by negative 5. That's going to give us 1, 1, and 0. Nothing changes there. So just divide everything through here by minus 5. And then it gets a little ugly. I think we're going to have to take 6 of these minus 5 of these. So 6 of row 1 and then minus 5 row 2s. Why do I do that? Because I want to get a 0. I want to get a 0 to match this leading 1 here. And that happens if I mix and match this 5 and the 6 with 6 and 5 multipliers. So 6 times this is minus 30, minus 30 is 0. 6 times this is minus 30, minus 5. So minus 30 plus 25 is going to be minus 5. And this minus 5 of these is going to be plus 5, like so. Okay, so now hopefully remembering RREF. I would like, this is triangular, is what we talked about before. It's row echelon form, but I also want first of this to be a 1 and this to be a 0 because it's in that same line. So let's do it in 2 stages. This has an obvious multiplier thing we can get rid of earlier on. So we're going to keep row 1 the same for now, 1, 1, 0. And then I want to take row 2 and divide it by -5, like I did the first one, to make this into a 1. So I can get 0, 1, this divided by -5 gives me -1. And now I'm in a position to get this one here to turn into a 0 because these are my 2 leading ones, little staircase. This one, though, because it's in the same column as one of the other leading ones, has to be turned into a 0. So I'm going to take row 1 minus row 2. That's going to give me 1 minus 0, 1 minus 1, 0 minus -1 is 1, 0, 1 minus 1. Row 2 stays the same. And boom, there's a solution. Our solution is I use the variables a and b. It's still the variables a and b now, but I can read off that a is equal to 1 and b is equal to -1. And does that make sense? I'm just going to go and slide that in here. If I put a 1 in here, and if I put a -1 in here, does that actually satisfy the equation? Well, -5 minus -5 is 0, perfect. And -6 minus -5 is +5. -6 plus 5 is -1. That works like a charm. We are good. And so we have our solution here. Oops, sorry. Whoops, that's not what I'm going to do. There we go. -1. So what we could say is if someone said, my basis is out of these 2 vectors, how many of each of them do I need? Well, I need -1 out of the first one and 1 out of the first one and -1 out of the second one. As long as I know what the basis is in terms of, I could just give you those 2 coordinates and say, yeah. It's 1 along the first thing and -1 along the second one. So that is how we can define coordinates in a new way. So I'm going to lock that and erase that. There we go. All right. Let me pause there. Let's actually draw it one more time. -1. We're going to do one more in the same vein before we wrap up for the day, but I just want to see if there's any questions about that example there, or if that makes enough sense for folks. All righty. No rush on the chat window there. Perfect. So we will do this last example, which looks a bit hairy. And let me just see if I can make it a bit larger. Oops. There we go. There we go. Right. Again, this is from the week 7. Sorry, selection lock. This is from the week 7 web work, so it'll be coming up. It's not immediate, but it gives you a flavor of what we're looking at. So this time we have polynomials. So I've got 4 plus 2x squared. I got this ugly stuff here. As a basis for P2. So this is all quadratic polynomials. All right. And if that's the case, we can build this other quadratic over here. We can build this quadratic out of these 3 building blocks. And this is, I'm not going to lie, going to be ugly, but you can see the structure of it. So i.e., if I take some amount a of the 4 plus 2x squareds and some amount b of the 12 minus 4x plus 6x squareds and some other amount or multiple of the 37 minus 8x plus 18x squareds, I can get this thing here. I can get 44 minus 16x plus 22x squared. Now, looks like a mess, I'm not going to lie. But wait a minute, what makes one polynomial equal to another? It's when all the coefficients of the constant, the x, and here the x squared is our highest term, when those coefficients are all equal. So if we do this in coefficients, what do we get? Well, I have an a times, let's do the constants. So the constants. I'm going to have a times 4 plus b times 12 plus c times 37 equals 44. To have the constant coefficient on the left-hand side equal the constant coefficient of 44 on the right, this is the equation I need to satisfy. For the x's, I'm going to have a times 0, because there's no x term here, it's only x squared, so that no a's, but b times minus 4 and c times minus 8 equals negative 16. And last but not least, for the x squareds, we're going to have a times 2 plus b times 6, that's a 6. Tweak that a little bit. And plus c times 18 equals 22x squareds. So I hope you see what we've distilled out of this thing by breaking it down into the constant x and x squared coefficients, constant x and x squared coefficients. I now have a system of linear equations with only a, b, and c in here. So even though there's quadratics in this thing, the equation that you end up solving is linear. And in fact, this has a nice expanded or augmented matrix form of 4, 12, 37, and 44, 0, negative 4, negative 8, negative 16, 2, 6, 18, and 22. And here you will really see the payoff of using the augmented matrix form in terms of being able to solve this equation and find out what a, b, and c are, which are the 3 components that they're looking for in the system here. So you're trying to fill in a equals, b equals, and c equals. And I'm not going to belabor this one because I've got another linear system that I'll leave as an optional thing at the end here. But you can see I can maybe divide this line here by 4. That's going to make it easier. Divided by negative 4, and it'll make it all positive. This line here can be divided by 2. And yeah, you'll be able to work through this system of equations. And again, we know there's going to be a unique solution. There will be a unique solution. We know that because the solution exists, because the set of functions here, let's call this f1, f2, f3. The set f1, f2, f3 spans P2. So there is a solution. Solution exists. And the set f1, f2, and f3 is linearly independent. We didn't prove that, but we were told that because we were told it is a basis. And so that means the solution is unique. If we have a basis, that means linearly independent set of building block vectors. And that means when I put those building block vectors together into a linear system and try to solve it, I'm only going to get a unique solution. Now take a look at these coefficients, the 4, 0, 2. That is just the coefficients of our constant x and x squared. 12 minus 4, 6. 12 minus 4, 6. So there's an analog, especially with polynomials, between just regular vectors in R2, R3, the stuff that we know and love, and how their coefficients work for polynomials. They work exactly the same way. So there's this funky analog between the two things. So yeah, I'll leave you to solve this. This again is part of your web work. So it'll be different numbers when you take a stab at it later on. We're at 414. What I just wanted to do at the end here was just give you some context for what kind of things do we ask, not only in web work, but also in midterms. So in midterm 2, a few years ago, and you can imagine we don't deviate too much in linear algebra classes between years. You can imagine something similar showing up on this year's midterm 2, which is not for a while yet. But hey, here's a 4 equation system with 4 variables in it, and I want to solve it. So what are you going to do? You're going to build the augmented matrix just like we did in those last 2 examples. Only here it's going to be a bit longer. And this is in the set of notes that was posted earlier. So what we're going to ask you to do is just translate this into, sorry, I should do it right myself, augmented matrix, to know what it means to translate. And it literally means grab the coefficients one by one and put them into a grid format in your augmented matrix, with the right-hand side values being everything on the right-hand side of that line. So shouldn't be news to anybody now. We've done 2 classes plus this class here touching on it. This translation of a linear system of equations to the augmented matrix form is just distilling away the coefficients, because we know implicitly they are multiplying each of these numbers in the matching column, in the corresponding column. So we have that mapping in mind. And then when we do row operations, what we're just acknowledging is, I don't need to know the x1 is multiplying this by this, because I only ever manipulate the coefficients anyway. So let's just work with the coefficients by themselves. Part B is literally just solve this. So turn this into row reduced echelon form and do the row operations, indicate what you're doing. So exactly what we did in one of the previous examples. And then last but not least, find the set of all solutions to the original system. So that was one of the major questions. I think there were 5 or 6 questions in that particular midterm. If you're able to execute all those steps and hopefully identify if you've made a mistake along the way, if something went fishy, if you're able to execute all the steps, though, that's a good chunk of the skills we're looking for you to be developing in the course. So I will write that one up just for your reference. I won't do it here live because it's not the most exciting calculation. I'd rather leave the floor open for questions afterwards. And also, again, wish you a happy reading week. It is now Friday at 4:17, and I hope you are free to enjoy at least a bit of break over the next 10 days. We'll see you back on campus after the 28th.